Today we have Guy Boyde talking on bounding size of homotopy groups of spheres.
Okay, thank you. Thank you for the opportunity to talk, Sarah, and thanks for coming, everyone. Yeah, so today I'm going to talk about bounding the size of the homotopy groups of spheres, and I guess maybe say at this point that the main thing that I hope will be a takeaway from this is that it's an advert for an open problem. You know, even by homotopy groups of spheres standards, which are low, we don't know a lot about the question of bounding size. So maybe a little more precisely, an outline of this talk goes as follows. Unsurprisingly, I'm going to want to state some theorems which do what the title says. And so that we're all clear going in, size means the most elementary thing that it possibly could throughout, which is after a little bit of a pirouette to get around the fact that the homotopy groups of spheres aren't always finite, we're going to find ourselves looking at a finite set. This is going to be the torsion subgroup. And I really do just mean cardinality, you know, as understood by, I don't know, shepherds for millennia or something. And then the second thing I'd like to do is try and convince you that making more progress on these questions is going to require new techniques in a sense that will be made moderately precise later on. Okay, so to get started, let's plant some definitions down. So my spaces are going to be based, although I don't say this here, but and given a space X, which will come with a base point, though we don't need to worry about that, pi q of X, or the qth homotopy group of X, is going to be the set of based homotopy classes of map from the q-dimensional sphere SQ into X. And part of the reason for saying this, I suppose, as well as fixing notation, is to flag to any stable homotopy theorists in the audience that I really do mean unstably here. This is the classical thing. The answers to these questions are going to turn out to be stable, but the questions themselves are unstable. We'll see that going on. Computing these things is you know, famously, infamously hard. And this is in really stark contrast with the homology of spheres, which is like a standard thing to do in a first course in algebraic topology, right? So here is a badly drawn schematic of the reduced homology of spheres. So I have an n-axis and a q-axis, and the thing in the n-qth entry is the qth reduced homology of the n-sphere. So the fact that there are z's on the main diagonal and zeros elsewhere is just telling you that HQ of Sn is z precisely when q is equal to n and is 0 otherwise. And my understanding of the history is that, like, back in the 30s, it was fully expected that the homotopy groups of spheres would be the same picture. And that's kind of half true. And it's half true as follows. So here's the equivalent picture for the homotopy groups. The sense in which it's half true is that on and below the diagonal, one still sees z's and zeros respectively. And above the diagonal, there's a bit more of a mess. And so, you know, the expectation that you ought to see zeros everywhere off the diagonal is up to a bit of hand waving. I'm being really imprecise here, saying that there shouldn't be any interesting maps between objects living in different dimensions. And saying that it's half true is saying that there are no interesting maps from objects of lower dimension to objects of higher, well, connectivity really, but dimension. Let's keep it simple. So, you know, if you want a silly sentence, this picture is saying that there's no such thing as an upside down version of cellular approximation where you explain somehow that maps from higher dimensional things to lower dimensional things ought to be 0. What could we notice here? I mean, maybe one thing that will be interesting later on is that you can see the prime 2 popping up, right? There are some Z mod 2s and there are some Z mod 12s, and the prime factors of 12 include 2. The prime factors of 12 also include 3. So we can see 2 and 3, but those are both quite small primes. So, you know, if we're going to find any larger primes, we're going to have to look further up. And that will come back to see us again later on. And the second thing you might notice is that all of the groups in sight are finitely generated abelian. And that turns out to be a theorem. So let's start there, because it's better to know something than nothing. So Sayre showed in 53 or so that that's a thing. So for all values of q and n, pi q sn is finitely generated abelian. That's a lot nicer than just knowing that it's a group, because, you know, groups can be really gnarly. They can be made of really awful pieces put together in really awful ways. But for finitely generated abelian ones, there's a really simple classification, which goes as follows. So such a thing, a finitely generated abelian group, is exactly a finite direct sum of copies of, well, 1, the infinite cyclic group, Z, and 2 cyclic groups of prime power order, Z mod P to the R. And I guess I'm sneakily fixing notation here as well as stating a theorem. So do take a moment to absorb it. And yeah, here are some examples of such things, right? So I could take a few copies of Z and direct sum on as Z mod 2. And I might more sensibly write such a thing as Z squared direct Z mod 2. And then this second example is going to be a good minimal working example for a lot of the things I'm going to want to say over the next few slides. So let's take a moment to look at that one. There's a Z mod 2, a Z mod 3, and a Z mod 9, where it's a little embarrassing to have to actually say this sentence, but the significant fact is that 9 is 3 squared. And so somehow at the prime 3, there are 2 things going on. The torsion comes in 2 different sizes. Right. Okay, so that's a start. We also know, let's flip back to this slide. So if one wants to know about these things, this breaks the question very naturally in 2. There is now an infinite piece of each homotopy group, some Z summans, and a finite piece, some direct sum of finite cyclic groups. And Serre also tells us exactly what the infinite piece is. That question is entirely resolved. So if you like, you can think of this as the computation of the rational homotopy groups of spheres. It's not the perspective we're going to take, but it is. So yeah, Serre tells us that these groups are torsion, which for finitely generated abelian groups is the same as being finite, unless, well, in the first case, Q equals n, or in the second case, n is even and Q is 2n minus 1. And in those cases, there's still only a single Z summand. So among other things, if we flick back a slide, that tells us that the first example can't occur as pi q s n for any values of Q or n because it's got too many Z summands in. It's got 2. Okay. But roughly speaking, the infinite summands are infrequent and well understood, so it's a good approximation to think of pi q s n as basically always being torsion apart from, I don't know, some important source terms in air quotes. What do I mean? I can make infrequent a little more precise. In the context of the theorem, that's just if you fix n, then you know, there's, depending on whether n is even or odd, there are either 1 or 2 values of Q for which the group pi q s n is infinite. And in those cases, there's still only a single Z summand. So a sensible version of the question from the title of the talk is, can we produce an upper bound on the size of the torsion subgroup of pi q s n? And almost always, that's going to be the whole group. So the title was a bit of a lie, but not very much of one. Really, we're talking about torsion subgroups, but they're almost always the whole thing. Does anyone have any questions about what I've said so far? I'll probably be very bad at stopping to ask, so do just interrupt. Okay. So yeah, so we have a well-defined question. What's next? So it's going to turn out that the machinery with which we attack this question is going to be, in some sense, factorized into primes. If you know what localization is, then that's what I mean, but I'm going to skirt it, try and talk to people who know less and assume that people who know more can fill in some gaps rather than vice versa. So I'll say a bit about that now. So given a finitely generated abelian group and a prime, the torsion subgroup is what it ought to be. It's all of the finite order elements. The P torsion subgroup is all of the elements whose order is a power of P. So importantly, that they don't have to have order exactly P, and maybe in that sense, the name is slightly misleading. Let's just quickly glance at an example to reassure ourselves that we know what's going on. So our favorite example from before, the torsion subgroup is the finite bit. It's everything you get once you've thrown away the Z. The 2 torsion subgroup is all of the elements whose order is a power of 2, which is just that copy of Z mod 2 there. And the 3 torsion subgroup is the Z mod 3 and the Z mod 9 together. And for other primes, the P torsion subgroup is going to be 0. So, for instance, there are no elements whose order is a power of 5 kicking around. Observation. the order of the p-torsion subgroup is always going to be a power of p. If there are any people who really like non-abelian groups in the audience, then a grotesquely overpowered way to see that is to say that it's going to be a Silov p subgroup, and consequence, its order is a power of p, but it's very easy to see from the classification. So let's take that more hands-on approach. Okay, so where does that leave us? We wanted to produce an upper bound on the size of the torsion subgroup of this guy, pi QSN. Now, the torsion subgroup is always going to be the direct sum of the p torsion subgroups as p ranges over, well, as it ranges over all primes. Although that's a bit silly because, of course, there are only finitely many Samans kicking around. So for all but finitely many primes, that's a 0, which is why that's a sensible thing to say. And this third bullet point is a bit loose. It suffices to bound the size of the p-torsion subgroup for each p as long as you do so in a way which gives you a finite bound on the size of the whole torsion subgroup. So we'll see that a bit later on, but for now, let's leave it at, we've decomposed the question of bounding into primes. And since we saw before that the order of the p-torsion subgroup is always a power of p, we may as well take log base p. This has the useful side effect of changing, okay, step back a bit. When you take a direct sum of two finite groups, the order is the product of the orders. After taking a log, that's going to become a plus, and somehow that makes the combinatorics easier to think about. It also, when one is dealing in upper bounds, makes your bound look better, which is quite nice, but it is quite a natural thing to do. So here we introduce some notation, which is going to follow us around for the rest of the talk. I'm going to denote by S sub p of NQ, the base p logarithm of the size of the p torsion part of pi QSN. So the S here stands for size. Maybe it's worth noting there's nothing here going on that depends on the fact that I'm thinking about something which is a homotopy group of a sphere. It would be fine to think about any finitely generated abelian group here. Yeah. And also, whatever this thing is, it's going to be in one-to-one correspondence with the size. It's just kind of like, you know, the homotopy groups of spheres complained that the exam was unusually hard this year, so we're grading them on a curve rather than asking about their actual size. But roughly speaking, it's size. Okay, let's think a bit about this thing, SPNQ, and see if we can get a sense of what it is. So let's just compute it for an example first. So here we have our favorite example again. The 3 torsion part of this group, like we saw before, was the Z mod 3 direct the Z mod 9. And so S3 of NQ is the base 3 logarithm of that. And I guess I'm writing it out this way rather than observing that 3 times 9 is 27. And I know what log base 3 of that is, just to remind us that, you know, log has this useful effect of meaning that the cardinality of a direct sum ends up being the sum. And you notice it's not hard to convince yourself that this generalizes, that this means that SPNQ is really asking the question, how many copies of Z mod P are you taking an extension of to get the torsion part that you're looking at? So here, the 3 torsion part is an extension of 3 copies of Z mod 3. You stick 2 of them together to get the Z mod 9, and then the second extension splits and gives you just an additional Z mod 3 Samand. Okay. And to think about that just a little bit more, let's take the point of view that we suppose we know SPNQ in some example. What does that entitle us to say about pi QSN? Well, there are 2 extreme cases, right? Either all of the extensions split or none of them did. So in this list of bullet points, really, I want you to look at the first one and the last one. So if you knew that SPNQ was 4, one extreme case is where you just have 4 direct Samans, all of which are Z mod P. And the other extreme is that you stack them all on top of each other to get a Z mod P to the 4. And everything can happen. Lots of other things can happen in between, but this is the picture. Okay. Right. So we've got to a point where we can state the results. The kind of chronology of this area is short enough that it fits on one slide, which is convenient. And of course, not all of these papers use the same notation, so I'm flattening a bit, but you knew that anyway, because that's how it always goes. The first person to ask about this question was Paul Seelig in a paper he wrote in 1982, which is quite short. And he's very explicitly here not trying to get a good bound. He's just trying to show that some finite bound exists. And the bound that he comes up with is 3 to the q squared. The sense I have of the second bound here, the paper a year later by Carl Friedrich Bodechheimer and Hans-Werner Henn, is that they read Seelig's paper and thought, we see how we can do better here. It's almost answering a question that's posed in that paper. And they take what was a quadratic exponent and turn it into a linear one, which is nice. That's good to know. And then Henn, in a solo paper a few years later, further improves on this. In this third case, this bound isn't the point of that paper. He's trying to do something different, and this paper is a technical lemma, this result rather, sorry, is a technical lemma that he needs on the way there. This bound has an important virtue, which I'll get to on the next slide, but for now, let's not worry about it too much. And then earlier this year, I got interested in this stuff and spotted a way to get the prime involved as well. And so for now, let's just say that the thrust of this fourth bound is if you take a bigger prime and ask about the p-torsion, then it grows slower. That's all that's really going on here. Okay, so let's make some first observations. Here are those last two bounds next to each other. Henn's bound, the second one, is the first stable bound. What do I mean by that? Well, it's a function of q minus n, which is the stem. It's a classical theorem, the Freudenthal suspension theorem, that if you fix the difference between q and n, q minus n, and let q, or equivalently n if you prefer, get really big, then eventually the group that you see stops changing. So somehow you'd like the bounds that you produce to have the same property. That is, if you fix q minus n and let q, or equivalently n, get really big, they should stop changing after a bit. And the simplest way that that can happen is if they just never change. They only depend on the difference q minus n. So that's a nice property. It's certainly not one, if we flick back, that the first two bounds had. If you walk up the stable range, it still gets bigger and bigger, which is not good. And then, so we'll see later on that none of these bounds seem to be at all close to the truth. But nonetheless, if I were really trying to sell you my one, I would say that a used car salesman would find reasons to charge you a bit more for it because there are a couple of cute extra features, though it's still not a very powerful result. Okay, what do I mean by that? Well, if you look at the middle version, the slightly stronger but less clean version of the bound, so this is the one with the 3 minus 2p appearing. Supposing that q minus n were less than 2p minus 3, that would mean that that fraction, the exponent on the 2, was negative. So you're raising 2 to some negative power. 2 to some negative power is something less than 1. So this guy SPNQ is bounded above by something that's less than 1. And by construction, it's the number of something. SPNQ was a non-negative integer. So being less than 1 makes it 0. And, if you raise p to the power 0, you get the size of the p-torsion part of pi qsn. And p to the 0 is 1. There's only one group of size 1. It's the trivial group. Which is to say that the bound kind of now knows the classical result that there is no p-torsion until the 2p minus third stem in the homotopy groups of spheres, which is quite cute. It happens just because you deduce the bound from the same kinds of machinery that you use to deduce that result from. So there's nothing particularly fancy going on, but it's nice that you can build that in. And the second bullet point here at the bottom is just how one to think about this. Well, I think about it kind of through this rearrangement, so that it's an exponential where the exponent is the stem q minus n, and the base is this p minus first root of 2. So even though we can still only bound by exponential growth, at least the base of that exponential gets arbitrarily close to 1 as the prime gets big. And this comes back to what we saw in the picture right at the start, right? We said, look, here's the homotopy groups of spheres in low dimensions. There are only 2s, and then a bit further out, you see some 3s. And it looks like bigger primes must take longer to appear. This kind of dignifies that a bit. It doesn't say growth is slower at larger primes. It says the best bound that we have is slower growing at larger primes. Okay, let's do an example. This example is slightly tongue-in-cheek. If one digs around a bit online, one can find a letter from the mid-70s that Grothendieck sent to Ronnie Brown. So this is kind of early on in Grothendieck's career, and his ideas, which later became extremely influential, haven't found much purchase yet. And he's complaining about this. And he says something like, I don't think homotopy theorists are going to care very much about this unless I show up with pi 147 of S123 as a byproduct. So there's a very tongue-in-cheek version of this talk that one could give, where you use as your title a partial answer to a question of Grothendieck. But that's for another time, perhaps. So yeah, so what can we say here? Taking the sharper version of the bound, Q minus n is 24. And we saw before that once the prime is large enough, the bound entitles you to say that there's no p torsion. And in this case, that's for p at least 11. When you go to the prime 7, you find that this guy S7NQ is at most 4. So what did that actually mean in real terms? It means that the 7 torsion piece of pi QSN of pi 147 of S123 is an extension of at most 4 copies of Z mod 7. You can go on, and it gets worse really quite quickly. It's completely disgusting by the time you're up to the prime 3. So you kind of wonder if these are very good bounds. The answer is they seem to be very far from the truth. We'll get to that in a bit. So yeah, so that's a first example. Yeah, how good are these bounds? How am I doing for time? A little quicker than I expected. Okay. Right. So here is a lower bound. Where does this lower bound come from? So Adams and others do some work on the J homomorphism and the E invariant, which kind of goes along with it. The J homomorphism we can think of as the identification of certain well-behaved families of non-zero classes in the homotopy groups of spheres. They happen in a pattern which is repeating kind of modulo 8, and that's a reflection of the fact that real K-theory is aperiodic, just as an aside. But what can we say? I mean, this is a kind of like grotesquely underpowered conclusion to draw from what you can actually say here. In particular, the summands that this work allows you to identify are always at one extreme of what I said SPNQ was doing. That is, they're a single very tall summand. So it's Z mod P to some large power rather than a large number of individual things. But that does in particular give you something about SPNQ. It's just a slightly weak conclusion to draw. So there are infinitely many values of Q minus n for which SPNQ exceeds this thing, which is a logarithm in the stem Q minus n. So now we've got an upper bound, which is an exponential, and a lower bound, which is a logarithm. Yeah, and we can compare this with known values. So this is what I mean when I said this talk was really, I mean, primarily an advert for an open problem rather than a claim that anything really cool has been deduced already. So Dan Isaacson and a couple of other authors whose first names I don't know have computed the first 90 stable stems up to some uncertainty at the prime 2. But certainly, for example, at the prime 3, we do know everything that's going on up to 90. And that's a good kind of initial portion of this sequence. We may as well compare, right? Given that our bound was stable, both our upper and lower bounds that we've seen are stable, we may as well take them and compare them with the true values in that range. And to give you a primer that the upper bound looks really awful in this setting. So there's clearly a lot more work to do. So the orange
what is
line.
the relationship between Julie's work, Goshen Wang's, and Asing's work and yours?
So this is just that among the things one is entitled to do given a bound, like the ones we've been discussing, is it applies to the stable stems. So it's like a bound on a sequence where the sequence is the true sizes of the p-torsion parts of the groups in the stable stems. And it makes sense then, since we do have this nice big initial portion of that sequence worked out in full, to compare.
I guess what I'm asking is, so like you mentioned that some of your bounds are stable bounds, and I was just wondering if like how close are your bounds to what the actual
right. Yeah, so I think the next slide will answer that. The answer is very far. So here, the blue line is the true values of this thing S3NQ. So here we're at the prime 3. The orange line is the exponential bound. So, I mean, you know, it's okay to begin with, and then being exponential rapidly becomes really bad. The gray line is the logarithm. So I didn't say that that was a lower bound. I just said that the true values exceed it infinitely often. So that will keep happening as you go further down.
So look, you said these are also these are bounds for the unstable homotopy groups that also end up being stable bounds.
Right. Exactly. Yeah.
Okay. So then, yeah, I don't. What happens when you compare this to what the actual, like, are the? I don't know too much about like unstable homotopy stuff, but like, do you know how this bound compares to like what the actual unstable homotopy groups are?
So no, I don't know. It's something that I should do. What might be worth saying is that they're known in a smaller range. So all of the unstable groups are known up to about because of course there are finitely many unstable groups in each stem. So it still makes sense to speak in terms of stems. They're known up to about stem number 40. And it was just going to be, you know, more work because it's still a 2-parameter family, whereas the stable groups are a 1-parameter family. So this was all done while I was preparing this talk. I hadn't actually thought about the comparison with the true values until.
That's super interesting. Thanks for.
That's okay. What else might be worth? So one, with respect to the families that Adams finds, so the ones that are detected by the E invariant, which happen with some regularity at odd primes. Basically what's happening, and this is kind of work due to Mahold at the prime, let me get this right way around, Mahold at the prime 2 and Gray at odd primes. So you have like some Z mod p to a big power in the stable range. And then as you step out of the stable range, the power will drop by 1, and it will drop by 1 more, all the way down to some sphere on which it's born. So typically, you should kind of think of there being a Z mod p in the 3 sphere, and you suspend that, and it turns out to be a multiple of 3. So there's a Z mod 9 on the 5 sphere. Yeah, double suspend. And it will keep going up until you hit the stable range, and you'll have attained some in the stems where we know about stuff that happens. Big caveat.
There was one thing I was curious about, like why is the logarithm of like the if you're working p locally, why is the p logarithm of the p torsion, why did that end up being a power of p?
I see. So why is the log in base p?
Yeah, why is that itself a power of a power? How is there a reason why it's the power of p?
Yeah. So what's happening there is that so you're seeing a value of SP which you can think of as growing linearly, but then you have to think about, you fix a K, and Adams tells you that you can find a Z mod P to the K summand somewhere.
Okay.
And then you ask him what stem that's in, and it turns out that the answer is proportional to P to the K. So the stem in which the class occurs is P to the the order of the torsion that you were asking for. And so when you flip that around and say, what's the relationship the other way around? Like once I've got to the something stem, how big is the torsion? It's gonna look like log. It's gonna happen infinitely often, but it maybe I didn't say that so good. Did that make sense?
Yeah, that makes sense. Yeah. Thank you.
That's okay.
Thank you.
And also thank you for the question, because I'm running very much under time at the moment. So if anyone has any other questions, there's certainly time to deal with them. Yeah, so we can guarantee that the blue line will remain below the orange line, and we can guarantee that it will peak above the gray line infinitely often. But beyond that, we don't know an awful lot. Finding lower bounds is kind of a bad idea, because you sort of expect that every once in a while it's going to drop back to 0. You know, that you don't expect the p torsion to kind of, yeah, you don't expect it to grow in that well-behaved a way. Though I can't on the fly think of a good shorthand for why one should believe that. Okay, let's see where we go from here. Yeah, so how might we do better? So what I really mean by how might we do better is, why does doing better require new techniques? And what I'm going to say in this section roughly is all 4 of the upper bounds that we know use essentially the same idea. And we can prove this kind of my theorem B, that within those constraints, it still looks kind of, you know, we can't prove a much better bound. But I'll try and make that precise slowly. Okay. So here it's going to get a little bit more technical. I'm going to kind of speak between speaking to the people who know a lot and the people who know a little less. So we're going to be localizing, and that's why it was natural that the results we had broke down into primes. It was because the EHP sequences are p-local gadgets. So everything that I'm about to say goes through odd primes too. It's just that the picture is more complicated there. So I'm going to tell you the 2 primary story, and hopefully you can imagine that it generalizes, but the basic idea is the same. You just need to work harder to make it work at odd primes. So there is a map which you can think of as some kind of Hopf invariant that goes from the loops on the n sphere to the loops on the 2n-1 sphere. And after localizing at 2, which is a functorial thing that you can do to spaces, but basically corresponds to taking 2 primary bits. It turns out that, so after 2 localization, the homotopy fiber of this map is the n-1 sphere, which is to say that we have a fibration that looks like Sn-1 to loops Sn to loops S2n-1. And fibrations give you long exact sequences when you take homotopy groups. But because I localized at 2 to get the thing I started with, that means that I get a long exact sequence on the 2 localized homotopy groups. Okay, so the key observation to kind of simplify this down to a pace that hopefully one can absorb in a talk is that if you take a finite, so finite actually, yeah, having no Z-Samans, finitely generated abelian group, then localizing at a prime is the same thing as taking the p-torsion piece. Because what happens is that torsion at other primes disappears when you localize, and the Zs turn into Z localized at whatever you localized at. But of course, if there were no Zs, then that is just going to be taking the p-torsion piece. So since Sayre told us that the homotopy groups of spheres are almost always finite, let's just for a moment pretend that they're always finite. And that therefore what I'm really saying in this theorem is that we have a long exact sequence on the 2 torsion components of these homotopy groups. We can forget localization entirely, or pretend that we can at least. Yeah, so I say that the odd primary version of this theorem is due to Toda, but is messier. In particular, there are 2 fibrations that get involved and everything trips up a bit. Okay, so we have this long exact sequence. Here is an observation. If I have finite groups and a 3-term exact sequence, so here I don't mean a short exact sequence. I'm not insisting that the first map be an injection and the second be a surjection, just an exact sequence. Then the cardinality of the middle thing is at most the product of the cardinalities of the other 2. So if it were a short exact sequence, then this would be exact. This would be inequality. But in general, we only have the inequality. Okay, so here I have an observation about exact sequences and an exact sequence. So it probably won't surprise you that the next thing I'm going to do is hit the exact sequence with the observation. And so doing, so again, here I'm pretending that the homotopy groups of spheres were always finite, just to simplify the picture, because this is mostly what happens. So if all the groups in this sequence are finite, they're just the bit we can see on the board, applying the observation tells us that the cardinalities of these groups behave like the observation. S2 was defined by taking the base 2 logarithm of the 2 torsion piece, and since the groups are finite, the 2 torsion piece just coincides with the 2 localization. Okay, so we get this inequality here where the product has become a sum because of the logarithm. That's nice. And in fact, that's almost all that one needs to do to get the foundation of this proof. The true picture is a little bit messier. And here is a lemma. This lemma, although I'm citing the second paper here because that's the one that gives it in something like this form, this is really what's underlying all of the work that anyone has done on this problem. And this epsilon 2, so this inequality is exactly what we had on the previous slide, apart from the appearance of this little epsilon term at the end, which is just what you need to control the Z summands, which don't fit into the framework outlined above because they're infinite, and everything I did was pretending just for a moment that we were thinking about finite groups. It might be worth noting just on the way past that our ability to control the contribution of these Z summands is actually really good. The fact that epsilon 2, this term is at most 1, is telling you that wherever you see a Z summand in the homotopy groups of spheres, it's kicking out, quote, at most a Z mod P. A priori, you have no reason to expect that it's not giving you a Z mod P squared or a Z mod P cubed or something even bigger that you have no expectation of controlling, but it's a single Z mod P. And I don't understand this very well, but it has to do with the fiber of the double suspension. And if you want to read more about it, I think the appendix of Huismoller's fiber bundles book has a weird out of place seeming section that deals with this kind of thing. It's quite interesting. Anyway, so there's this lemma, which we extract from the topology in basically the way outlined above. You have a fibration, and you know that cardinality behaves quite well in long exact sequences, so you can do this, right? So this brings us around to the need for new tools. So I'll say the theorem informally, and then I'll circle back and try and explain what I mean by it. Any bound on these guys SPNQ, which can be deduced by doing, quote, better combinatorics on the same topology, grows at least like this thing, right? Don't worry about the details. What's important here? Well, the shape of it is roughly like the last bound I gave you, right? The one from my theorem, in the sense that there's a base, and then the exponent looks like Q minus N divided by something linear in P. So qualitatively, it's roughly the same, although it is a bit better. So what do I mean by doing better combinatorics on the same topology? I mean, if we flick back to the previous slide, that the topology that we have gives us this lemma, and then we do combinatorics on it. There are values of S2, or more generally at odd primes SP, which satisfy the restrictions placed by this lemma, but grow like this exponential that I have here, and provably so. The golden ratio isn't doing anything fancy. Maybe it shouldn't surprise you, given that we have the lemma in the form that we do here. It looks a bit Fibonacci-ish. Indeed, there is a Fibonacci sequence hiding somewhere that is the worst this could possibly be. Okay. So yeah, so within the constraints placed by this lemma, which represents the topology that has been done, it could still be exponential. Doing better within this framework, so finding a better bound, a better than exponential bound, would involve finding some kind of systematic way to control the boundary maps in the EHP sequence. And in order to see that briefly, I'll flick back a slide or two. Right, so here was the exact sequence that we had. And the cardinality bound was going to be an equality if this sequence was short exact. That would be if the long exact sequence split. But we'd really like it to be very far from an equality. We'd like to be able to say that the cardinality of the middle thing is much less than the product of the outer two things. And that would involve saying something about the maps in this sequence without making it too precise. Yeah, so within the current framework, you'd need to be able to say something systematic kind of about the rest mass of the system, about the way the boundary maps behave on a large scale. But frankly, I have no idea. It may well be that new techniques entirely are required, and who knows? Yeah, so the end on the open question, right? We know it's between exponential and logarithmic in some sense. It's less than exponential and infinitely often pops back up to being at least logarithmic. But we really don't know what the growth of SPNQ looks like. Yeah, I think that's everything I had to say. Thank you very much for your attention, everyone.
On behalf of everyone, I'd like to thank Guy. Are there any further questions?
I have a question. Hi, Guy, it's Seb.
Hi.
Can you give us any more insight as to what these weird, funky new methods could be? Do you have any indications, or is it purely speculation right now?
No, I mean, I can see that new methods are needed. It's a world away from knowing what they ought to be. Yeah.
So no guesses either.
No guesses.
Okay, cards very close to the chest, I understand.
I have another question. So this is Jens from Münster. What if we actually would like to distinguish between, say, Z mod P times Z mod P and a Z mod P squared? Do you know any methods that would be able to say something about that? I mean, in particular, is it true that for every prime P, there's arbitrarily big powers of P showing up in the P torsion subgroups?
Right, so I can be a bit more precise about that. So the exponent problem, that is, if you fix a sphere and look at pi star Sn, so all of the homotopy groups together, the biggest power of P showing up is completely known at odd primes and remains open, but only in a narrow way at the prime 2. So at odd primes, at least after looping, an even dimensional sphere decomposes as a product of odd dimensional spheres. So the problem is reduced to odd dimensional spheres, and the P primary exponent of S2n plus, it's either plus or minus 1. I'm going to say S2n plus 1 is P. Oh, is P to the n, sorry. Which is to say that, so you look at S3, there are classes of Z mod P, of order P there, but none of order P squared. You look at S5, now there are classes of order P squared, but none of P cubed. And S7 has classes of order P cubed, but none higher. So the exponent problem for spheres is completely resolved at odd primes. So you can place some restrictions that way. In the first place, which is which is hard. I'm not sure how well that answers the question. But certainly the methods you use to attack size are much closer to the ones that you would use to attack rank, that is the number of summands, than they are to the ones that you would attack torsion depth, so exponent. But yeah, so Cohen, Moore, and Neissendorfer sometime in the mid-80s. And yeah, I think they're roughly under that title. If you look for the exponent problem for spheres, that's the magic words to Google.
Yeah, I was wondering about that. I was wondering if this problem of showing that there's something of order, if there's an element of a certain order in the homotopy groups, yeah. If you could use Neissendorfer's results about exponents in Moore spaces.
Yeah, one certainly can. I haven't seen a way to join this on here, but
yeah. It's, I don't know, it makes you happy to know that someone's thinking about this. Yeah.
All right, well, if there are no further questions, I'd like to thank Guy again. I'll go ahead and stop the recording.